Welcome to the Knowledge Graph seminar. Today we are in the week 6 of the course. So far in the course, we have defined what a knowledge graph is, and we spent a few weeks talking about how to create a knowledge graph from the structured data, from unstructured data. And now we are getting into the next segment of the course where we will be looking at how we can reason with and access a knowledge graph. This week, our focus is going to be on the inference algorithms. And then in the following weeks, we'll talk about how do users interact with the knowledge graph and how a knowledge graph changes over a period of time. So today's presentation will be divided into two separate segments. The first one is going to be theoretical or the algorithmic part of the presentation, where I'll describe various knowledge graph inference algorithms. And in the second part, I will illustrate how some of those algorithms are used in solving real problems in the analytic settings, in the actual business use cases. Okay. Originally, I was hoping that the part 2 of the lecture I would give during week 8, but during week 8, we were able to find some really exciting speakers. So I decided to combine these two lectures into one, and that I thought would be more effective because it's more interesting to understand these algorithms in the application context. Okay, so with that, let's start with our discussion on what are some of the knowledge graph inference algorithms. Early on in the course, I introduced Sparkle and Cipher as query languages. And the examples for these two query languages that I gave, they were fairly simple and very preliminary. And the examples primarily illustrated how we can retrieve the information or look up the information which already exists in the knowledge graph. With knowledge graph inference, we are interested in deriving new conclusions which are not explicitly stated in the knowledge graph. And there are many different ways of doing it. And we will look at families of such inference algorithms. At the highest level, I will consider two broad families of algorithms, the graph-based inference algorithms and ontology-based inference algorithms. The graph-based algorithms, they originate primarily from the pure abstract graph algorithms, and ontology-based inference algorithms, they come from the field of knowledge representation and reasoning. There is a huge variety of graph algorithms that could be used on graph structured data. In fact, there are books dedicated just to graph algorithms. For the purpose of our lecture here, I have chosen to focus on three families of graph algorithms: pathfinding, centrality detection, and community detection. And I'll go into detail for each of these algorithms. Pathfinding is a basic operation on a graph. Given a graph which we are seeing here, in which the edges are labeled by numbers, where numbers represent the cost of going from one edge to one node to another node. So given a graph like this, the path finding problem is to figure out what is the cheapest way to go from one node to another node. So for example, if we are at node A and we want to calculate the shortest path for going to node C, we could either go from A to C directly, which has a cost of 5, or we could go from A to D and D to C, which has a cost of 4. So in this case, we would prefer going from A to D and D to C. And there are obvious applications for this kind of calculation in applications such as traffic planning, where when you are navigating, you want to figure out the shortest way for getting from place A to place B. The pathfinding problem can be framed in many different ways. One way this is framed is that you are given a single starting node, and from that single node, you want to figure out shortest path to all other nodes in the graph. So this is known as a single source shortest path problem. So in this case, I'm illustrating that our starting node is A, and we want to find shortest paths from A to B, A to C, A to D, and A to E. Okay. Another variation of the pathfinding problem is minimum spanning tree. It's also sometimes known as trip planning or traveling salesman problem, where we want to start from one node and we want to visit every other node such that the overall cost is minimum. And the relationship to traveling salesman is that a salesman has to visit certain number of cities, and they want to do it in a way that their overall cost is minimum. So there are many approaches for doing the pathfinding, but I'm going to cover a classic algorithm for solving the pathfinding problem, which is known as A-star algorithm. It's a very fundamental algorithm which was originally developed in the context of AI planning, but it's clearly applicable to doing pathfinding in the graphs. So the basic approach taken in this algorithm is to maintain a tree of paths from the starting node, and those trees of paths is extended until the termination criteria is met. And that extension is based on an estimate of the length of the path if we traverse a particular edge. And the way that is calculated is if Fn is the cost of reaching the end goal, and Gn is the cost that we've already incurred until now, and Hn is an estimate of what would be the cost if we follow a particular edge. Hn here is clearly an estimate because we have not reached our end state, so we don't know what the exact cost is. Hn is simply an estimate, and that's why it is known as a heuristic. Okay, it's a heuristic, and in particular, we are interested in a certain class of heuristics which are known as admissible heuristics. And admissible heuristic is a heuristic which never overestimates the cost. It could underestimate the cost, but it never overestimates the cost. And there exists a proof which shows that as long as our heuristic is admissible, we will end up with an optimal path at the end of our search process. Because of the heuristic nature of this algorithm, there is a ton of work on it. And there have been books that are written on just search algorithms or A-star type algorithms. But for our discussion here, I'm going to illustrate the working of the algorithm using a very simple case where we assume that our heuristic is simply 0, right? And obviously, if we assume that the cost of reaching the goal state is 0, it is clearly not a overestimate, right? It's clearly not an overestimate. And when we set the heuristic to 0, the search algorithm also degenerates or reduces to what's more popularly known as a breadth-first algorithm or Dijkstra's algorithm. So to illustrate the working of this algorithm, we will illustrate the process when we are trying to calculate the shortest path from node A to node E. So when we start from node A, we first enumerate all possible choices. We could go from A to B, A to C, and A to D. And among these three choices, the shortest path is, or the least cost is if we traverse the node D, like we go from A to D. So in the first step, we will choose to go from A to D. And then at D, we will explore all the options. We could either go to from D to C, or we could go from D to E. Now, even though E is our goal state in this case, but the cost of going from D to C is 4, which is less than the cost of going from D to E. So in this case, we would still want to explore, because it is quite possible that if we go to C and then for going from C to E, the overall cost is less than 5. We don't know that, right? So in this case, then we have to go and explore C. And we realize that if we follow that path from C to E, the cost is actually going to be 6, and therefore the path that we have already found from A to D and D to E, that is the shortest path for going from A to E. Okay, so that was sort of a quick walkthrough of how the A-star algorithm works for the case where the heuristic is set to 0. And as I had mentioned previously, the algorithm, it's a very well-known pathfinding algorithm, and it has a ton of applications. Originally, it was introduced in the context of AI planning, but now its applications are way beyond just AI planning. All right, let's now talk about centrality detection. The basic idea behind centrality detection algorithms is that they help us in understanding the importance of a node in a network. So given a graph or graph kind of structure, we want to figure out what nodes are most important, or what nodes in a way are bridges, so that they are salient in the sense that they connect lots and lots of other nodes. Those kind of analysis or insight can be very useful in identifying bottlenecks or vulnerability in a complicated graph structure. So just to illustrate different methods for checking centrality, a simple approach is to simply count the degree of a node. By degree, we mean how many other nodes that a given node is connected to. So in this graph that we are seeing here, node A is connected to highest number of other nodes. And so in this network, A is a central node based on the degree centrality metric. Betweenness centrality is another way to calculate centrality in a graph structure. And a node is considered to have high betweenness centrality if it has the largest number of shortest paths going through it. So in this complete network structure, node B is at a point so that a lot of shortest paths would pass through it. We know that in the cluster of nodes shown to the upper left and to the bottom right, there are other nodes which might be central in terms of shortest paths going through it. But if you take the overall graph, B has this unique position where if we were to calculate shortest paths among all the different nodes, a largest number of shortest paths would be passing through B. And in this case, B has the highest betweenness centrality based on that metric. Then another metric for calculating centrality is known as closeness centrality. And closeness centrality is defined as the node which is closest to all the nodes in this network. Okay. Now, in this example, to illustrate the closeness centrality, we are going to consider just that fragment of the graph which is to the rightmost part of the slide. We're not considering the whole graph. We're just considering this little fragment to the right. And in that fragment, node C has the highest closeness centrality because it is closest to all the nodes in the graph. And again, underlying, obviously, you would have to calculate the shortest paths, and then you'll have to figure out which node is closest to the most number of nodes. But at the highest level, the definition is that C is a node which is closest to all the nodes in the network. The fourth and final metric which is used for centrality detection is known as page rank. Now, this page rank originally was developed in the context of information retrieval, and Google is the company that is the heaviest user of this. And Page here actually stands for Larry Page. That's his last name. And originally it was used to figure out what web pages are the most salient over the web. But given that the web of documents on the internet defines a graph structure, this kind of rank can be applied to any graph structure. And the nice thing about this algorithm is that it is designed to take the importance of the nodes into account. So for example, if a node is connected to lots of influential nodes, then it is probably more central than a node which is, even though connected to lots of other nodes, but it's connected to all these trivial nodes, right? And that kind of thing actually made sense, and it made perfect sense to use this in the context of web search. So given the importance of this algorithm, I thought it might make sense to look at it a little bit more closely. And as I was saying earlier, the basic idea here is to take into account the uh, the influence of other nodes on a given node within the network. And the algorithm is iterative, and it's built around this formula that you are seeing here on the screen. And I'm going to walk you through this. On the left-hand side of the equation, we have page rank of a node U. We are calculating the page rank of a node U, which is sum of 1 minus d plus d multiplied by this larger expression. D here is known as a damping factor, which actually is the likely, in the web context, it is the likelihood of visiting a node directly versus visiting it by following link to other pages. Typically, its value is set to 0.85. Let's just look at the expression that we are seeing within the parentheses. So PRT1 through PRTN, they are the page ranks for nodes T1 through Tn. And CT1 through CTN is the count of number of other nodes that each of these is connected to. So the way this algorithm works is that we would start by setting the page ranks for all the nodes to some arbitrary value. It could be even just 1 divided by the total number of nodes in the networks. And at each step, we would update the values. And we will keep doing this until the algorithm stabilizes. And again, this is an iterative algorithm, but it seems to work very well for web search. And it's also used quite a bit for identifying central nodes in a complex graph structure. All right, let's now move on to the third category of graph algorithms for community detection. So the basic idea or the requirement for community detection is to identify the nodes in the graph that go as a group. They are closely connected based on some criteria. And in general, the nodes which are in the same community are going to have more relationships among themselves to the nodes which are not in the community. And many times, community detection is also used as the first step in a two-phase analysis process. So what you want to do is, given a graph, first find out the communities, and that's your first step. And once you've identified the communities, then you just want to focus your analysis on every node which is in the community and go drill deeper into what's going on within that community. So we will now look at some of the algorithmic techniques which are used for community detection. There are two broad families of algorithms for community detection. There are standard graph algorithms, and then there are bottom-up algorithms. So as an example of a standard graph algorithm, we will take this sample network that we see here. And one basic thing that we can do here is to identify connected components. A connected component for a directed graph is essentially a set of nodes such that in the underlying undirected graph, you can go from every node to every other node. Okay, and it's one very simple basic measure of identifying communities in a graph algorithm. Sorry, in a complicated graph. Second, very common standard graph algorithm is strongly connected components. And strongly connected components, of course, are computed in relation to directed graphs. And a set of nodes in a directed graph is strongly connected if it is possible to go from A to B, and for every pair of nodes you can go from one to the other and back to the other one. And in the picture shown here, we can see that there are two set of nodes which are strongly connected to each other. And in this case, we would say that this graph has those two group of nodes as communities. Next, let's talk about bottom-up algorithms. And even within bottom-up algorithms, there are two common approaches, which are known as label propagation and unfolding. And I'll give you a quick sketch for each of these algorithms just so that you get a feel for how they work. So in the label propagation algorithms, we start by assigning each node in the graph to a different community. And then we fix an order in which we are going to examine all the nodes and update which community they belong to. And when we examine all the nodes in a given fixed order, we examine one node at a time. And the way we update its community is we would examine what are the communities to which its neighbors belong. Okay. And in some cases, there may be there may be a tie. Like, for example, if a node has only two neighbors, one of them belongs to community A, the other one belongs to community B. So there is no way to sort of prioritize one over the other. In those cases, we break the tie randomly and we would update the community of that node to the community of one of its neighbors. Okay. And we would keep repeating this process until we reach a condition when each node is in a community which is shared by most of its neighbors. Okay. Again, this is a bottom-up process. It's a emergent algorithm because when we start, we don't know what communities we are going to end up with. And that's why this kind of algorithm is very compelling for doing graph analytics, because it tends to reveal patterns which we may not even have thought of. In the same family of algorithms, there is another very popular technique known as the unfolding algorithm. And some people also call it like a Louvain algorithm, which is the name of the person who originally introduced it. So just like the previous algorithm, we initialize the first step of this algorithm, we initialize that each node is going to be in a separate community. And then we are going to examine each node and its neighbors to test if there will be an overall gain in the modularity by placing it in the same community as a neighbor. So here, we are not doing automatic changing of the community. We are making that decision based on a formula. And there are many different ways of defining what the overall modularity score would be if we make the change. But here's one sample formula that I'm showing, which is used for calculating the overall modularity of the graph. We can briefly look at how this expression is computed. So we have k communities. So we are computing the modularity score for each community, and we are adding them up. And the way we compute the modularity score for each community is in the first term, we are taking the number of nodes in the community and we are dividing it by total number of edges. And then in the second term here, we are taking the total degree of all the nodes in that community and we are dividing it by total number of edges. So that's a kind of a measure of how modular the graph is. And if by making a change in the community setting of a node to its neighbors, if the overall modularity score of the graph is going to improve, then we make the switch. If the modularity score will not improve, we won't make the switch. So we keep doing this process until it stabilizes. And And then there's a phase two of the algorithm in which we would create a new graph in which every node in this new graph represents a community from phase one. Okay. And if there are edges between nodes in two communities in the phase one graph, we would represent that as a self loop. If there is an edge that goes from one community to the other community, then there would be edge in this phase two graph to capture that. So basically in phase two, we have a condensed version of the graph that we originally started from. And once we have this condensed version of the graph, then we would repeat the phase one process on this condensed graph. And the process, we will keep doing this until the process converges. All right, so that was a whirlwind tour of graph-based algorithms. And next, I'm going to talk about ontology-based inference algorithms. And I like to think that the key differentiator between a general graph system and a knowledge graph system is actually the ontology-based inference. Because all the algorithms that I talked to you about until now, they could be applied to even an abstract graph, right? It doesn't have to be within quotes a knowledge graph for us to use those algorithms. When a general graph starts to become a knowledge graph when we start to add semantics, semantics of the application domain. And typically we add semantics of the application domain with a graph is by associating classes or defining the semantics of how the nodes are connected to each other and defining the semantic properties of the relationships. So when you start adding this kind of semantic knowledge or domain knowledge to a graph, there are algorithms which you can label it whichever way you like, but I chose to label it using ontology-based inference. And within that, I'm making two further distinctions. One is class-based inference, or you can think of it as taxonomic reasoning. And then the second one is rule-based inference, where you are driven by a set of rules that you're going to apply against your data. Now, the distinction between the class-based inference and rule-based inference is not very sharp. Sometimes it's primarily a matter of implementation choice. Some people would say that, well, you can do all kinds of class-based inference using rules. And under certain circumstances, that may be correct. But one thing I do want to point out is that in the implementation of the many class-based inference systems, they would tend to make more direct use of the graph-based algorithms I talked about in the previous segment. So for example, if you were doing some taxonomic reasoning, you would do graph traversal, and of course you can do graph traversal using rules, but in a ontology or in a taxonomic based system or class based system, they would more directly tend to leverage the graph algorithms. Okay, let's now look at each of these two types of reasoning in a little bit more detail. The taxonomic reasoning is applicable or useful when it is useful to organize the knowledge into a set of classes, right? I mean, there are applications where it may not make sense to organize things into classes. So like, let's say you had a graph representing nodes on the internet, and that's all you care for. There are hardly any classes there, right? But on the other hand, if you wanted to model the graph of relationships, say in Wikipedia or Wikidata, then suddenly, it becomes more interesting to organize your facts into a set of classes. And classes are nothing but unary relations or types. And when you have classes, we can define class membership, we can specialize the classes, and we will look at each of these features in a little bit more detail so that you have more of a feel for how this is done. Now, it turns out that both property graph data model and RDF data model they support classes. And in the property graph data model that we have considered earlier in the class, the node types essentially function in the same way as classes would. And in the RDF data model, they have a RDF schema layer in which they let you define classes, and they would also let you define domain and range constraints over your relationships. And as I have previously noted, RDF is sort of the lowest representation layer in a sequence of languages. And they, in principle, could extend their basic representation to have a full-fledged ontology language or a rule language. But for the purpose of the discussion in this lecture, I've chosen to keep the discussion independent of these models. Right? I'm going to present the basic fundamentals of the inference without referencing either RDF or property graph, because the concepts or the basic inferences that you can do, they are independent of which data model you use. And obviously there could be some specific differences when you get into the details of a model, but for the purpose of the course, I felt that it was not critical to get into those differences. Okay, so let's take a very simple example where we have people. We have male and two kinds of people, male and female. We have male of Art, male of Bob, and we can represent them in two different ways. We can represent them as unary relations, such as male of Art, or we could say male is a class and instance of Art male, right? You can, the two are equivalent. Logically, they mean the same thing. Okay, so given this kind of very simple example, we can organize our knowledge into a hierarchy. So we can make assertions such as female is a subclass of person, male is a subclass of person. Okay, so when we have these subclass relationships in our knowledge graph, we can do the first very simple inference that we can do is the transitivity inference. So for example, if A is a subclass of B and B is a subclass of C, we can conclude that A is a subclass of C. Okay, and then subclass and instance of are also related to each other, and the rule shown next captures that relationship, which essentially says that if A is a subclass of B and A is a subclass of B and I is an instance of A, then I must also be an instance of B. Okay, so this inference would naturally follow from the definitions of subclass and instance of. We can declare that classes are disjoint. So for example, we could say that male and female are disjoint. And if two classes are disjoint, then they can't have any instances in common. And this can be used for a variety of inferences in a knowledge graph, but most basic form of inference which you can do with this is to make sure that things are defined appropriately so that we don't put same thing in two different classes that happen to be disjoint. For these classes, we can introduce class definitions, and the class definition has usually two components. There are necessary properties of a class, and then there are sufficient properties of a class. The necessary properties of a class are all those properties that are shared by the instances of that class. So for example, we could say that if we have a class brown-haired person, then all instances of that class are going to have a hair color of brown, right? So in using the rule which we are seeing on the screen, we are specifying the properties of all the instances of the class brown-haired person. The sufficient property of a class lets us conclude that a particular instance is a member of that class, right? So for example, if we had a class brown-haired person, we could say that any person whose hair is brown must be a member of or must be an instance of that class, which you can see in the rule shown below. Now, from the sort of logical syntactic structure of these rules, the main distinction is that in a necessary property, you would have instance of appear in the body of the rule, and in the sufficient property, you would have a rule in which instance of appears in the head of the rule. Because with a sufficient property, you're concluding a class membership, and with a necessary property, you're using the class membership to derive a new conclusion. Okay. Now, we were talking earlier about defining the semantics of the relationships in a knowledge graph. And the basic semantics you want to define for the relationships are the constraints on the first argument and the second argument. So the constraint on the first argument is usually referred to as domain, and the constraint on the second argument is referred to as range. So for example, if we had a parent relationship, we could state that if X is a parent of Y and X doesn't happen to be an instance of the class person, whereas domain of that class parent is person, then that's illegal. Okay, and similarly, we can define the constraint on the second argument, which is usually referred to as the range of the relation. In addition to these type constraints, we can also have cardinality and the numeric restrictions on the relations. So a cardinality restriction limits the number of values that a relation can take. So for example, we could have a constraint which states that a person can have exactly two parents. They cannot have more than two parents. And then we can also put restrictions on the numeric values. We could say that a person, the age of a person cannot be more than 125. Okay. The inference which is used quite heavily in the taxonomic system is called inheritance. And what that basically means is that once you define the class hierarchy, we've defined these relations. Relation values are set to inherit to the instances of the class, right? And we've seen some examples of this previously. And one of those examples was that if Art is an instance of the class brown-haired person, then we can conclude that Art is going to have brown hair, regardless of whether it was explicitly stated in our data or not. But more broadly, in the taxonomic system, there are 4 categories of inferences, each of which has different difficulty in terms of the complexity of performing them. And the most difficult of those is the first one, which is given 2 classes A and B, figure out whether A is a subclass of B. Here we are primarily working from the class descriptions, and we have to do inference at the level of class description. In the second inference, which is known as also known as classification. Actually, the first one is usually known as subsumption. The second inference is known as classification, where we are given an instance I, and we want to figure out if I is an instance of the class A. So the main difference here is that from the first one is that in this case, we are given a concrete instance, and then we are trying to compare it against the description of a class. In the third one, we are given a ground atom. It could be something very simple as whether Art has brown hair, and we want to check whether it's true or false. And finally, the fourth inference is also known as query processing or query answering. We are given a query, and we want to figure out what are the different values of the variables in that query, which is going to make that query true. Okay. So again, this was sort of a whirlwind tour of taxonomic inference. And as I noted previously, the boundary between the taxonomic inference and rule-based inference is not very sharp, right? I've made that distinction in this lecture primarily for pedagogical purposes. But if you were going out to actually build a system, then you could go many different ways. You may or may not choose to make that distinction. Okay, so to explain the rule-based reasoning, I'm going to take an example. And the reason why I've chosen this example is just to sort of capture the complexity, which is inherently more complex than just being able to define taxonomies and relations and constraints. So in this on this slide, you are seeing a property graph representation of a domain. And I'm going to read this for you. First, I will read the top part of the slide, where we are saying that we have a node type person, and that person is involved in a study. And that study is about chemicals. Okay. And now let's read the bottom half of this property graph, where we are saying that a company produces a product, and that product can contain chemicals. Okay. And then there is an edge which is going from company to a person, which is labeled as funded by. Okay. So that's a very simple property graph model for a given domain. And given this model, we would have instances which populate this property graph model. We want to conclude conflicts of interest. So what are the who are the people who have conflicts of interests in being involved in certain studies? So to capture that conflict of interest, rules are a very good device, and I'm showing here example rules using which we can do that. The first rule here is simply calculating the interest of a company in a particular product. And what this rule is essentially saying that a company X has interest in a product Z if that company X produces Y, and then Y contains Z. Okay, so I actually misspoke. A company X has interest in chemical Z if company X produces product Y, and that product Y contains chemical Z. Okay. And then in the next rule, we are actually defining the meaning of conflict of interest. And what does actually conflict of interest mean? And we say that a person X who is involved in study Y has a conflict of interest with company Z if X is involved in Y, in study Y, that study Y is about a chemical P, and that person X is funded by Z, and Z happens to have an interest in P. Okay, so it's a fairly intricate relationship between these different nodes in this graph to calculate this conflict of interest, and rules give a natural abstraction or natural way to capture these relationships. Now, in this example, if we use a rule-based approach to doing the inference, the conflicts of interest that we would derive, they would not live in the knowledge graph. But it doesn't have to be that way. Some people would say that, well, I want the result of my query to also be a knowledge graph. I want to calculate the result, and then I want to put the result in my knowledge graph. Now, for those of you who have been in this course, you know that how big a deal I made about the fact that in knowledge graphs, your relationships have to be binary. And in this case, the head of the rule is not a binary relationship. So you somehow have to, if you're going to capture the conflicts of interest in your knowledge graph, you have to come up with some approach. And in multiple lectures, we talked about this idea of reification. Okay, that if we wanted the conflict of interest actually incorporated into the graph, we would have to reify this conflict of interest relationship. And that reification also we can capture using graphs. And as you know, the basic idea in reification is that for any non-binary relation, we would have to create a new object, right? And in this case, we are introducing that object by putting an existential in the head of the rule. And here we are introducing a new object C, which represents the conflict of interest. And then for that new object, we introduce a set of relationships which capture different components of the relationship. And here we are introducing relationships: conflict of, conflict reason, conflict with. And we say that the conflict of C is X, conflict reason is Y, and Y here happens to be the study, and conflict with is Z, which happens to be the company. Okay, so so this is an approach to define complex inferences which we want to perform over the data which sits in our knowledge graph, and express them using rules. And if we want to represent the conclusions also within the graph, then also specify that addition to the knowledge graph using something like existential rules. Okay, now this is sort of only one slide overview of how we actually apply the rules. And in general, there are two strategies for applying rules against the knowledge graph. There is a bottom-up strategy and there's a top-down strategy. In the bottom-up strategy, we apply the rules against the data, and we would derive new facts, and we will add those new facts into our database. And we keep doing this until we cannot derive any more facts. And obviously, one complication that would arise in this approach would be we have to make sure that our calculation ends. We should terminate at some point. And there are approaches to ensure that, sometimes through the restriction on the language, and sometimes through restrictions on the algorithm to make sure that our calculation is going to stop. The nice thing about a bottom-up strategy is that once we've applied all the rules, now we all have just more facts, and then we can use our traditional query processing algorithms on that derived data to answer the queries. In the top-down strategy, we start from the query, and we only apply those rules which are required. We don't conclude everything. We conclude only those things which we might actually need in answering the query. And in this case, we do need a much tighter integration between our rule engine and the query evaluation engine, right? In the previous approach, once we had applied all the rules, query engine could just work separately, right? But here, the two have to work in a close cooperation with each other. The nice thing about a top-down strategy is that we'll obviously require less space, because we're not going to derive everything. We're going to derive only those things which are required. Now, for doing this rule-based inference, there are many efficient and scalable rule engines available today. And in fact, for our Thursday lecture, we have a guest presentation from a company called Relational.ai, who have been building a rule-based reasoning engine, and we'll be hearing from them in a lot of detail about how they went about building their engine and how their engine helps support reasoning over knowledge graphs. All right, to summarize, the knowledge graph inference algorithms at the very highest level, they fall into two broad categories: traditional graph algorithms, which are things like pathfinding, centrality detection, community detection, and the ontology-based algorithms or semantic algorithms, which can be either taxonomic reasoning algorithms or rule-based reasoning algorithms. So with that, I conclude the first part of the presentation, and I'm ready to go into the second part. Should we look at the question, or should we just go right into the second part? There's one question from Sudhir. In description logics, domain and range are not constraints. Any thoughts on the pros and cons of the domain range semantics of your KGs versus that in DLs? Well, so, my short answer to that question is that I prefer the logic programming style definition of constraints as compared to the description logic style semantics. And as you know, description logic semantics are based on Tarskian semantics, and it requires you to think of possible worlds. And I'm not sure if that's the most appropriate way to think about the world. In logic programming, we are advocating the use of Herbrand semantics, where semantics are defined in relation to the data that you have. And then defining them, domain and range as constraints, that seem to make more sense. And that's the kind of approach I personally prefer and advocate. So I hope that satisfies Sudhir's question. All right, so I'm now ready to launch into the second part. We have plenty of time left to go through this, and hopefully still we'll have time at the end for more discussion. So knowledge graphs have a lot of applications, and these days they are being used in all kinds of domains. And one interesting example that I recently stumbled into was Marvel Comics. They have tried to create a knowledge graph for Marvel's cinematic universe. And basically each node is can be a character or a particular movie, and then they have edges which have semantics like whether two characters appeared in a particular movie together, and whether two characters appeared in a particular scene together. And they're using this graph of their characters and movies to better understand their current movies, as well as to help design new movies, like to think or look for connections that are currently missing in their knowledge graph to figure out what new movies they could come up with. There is International Association of Investigative Journalism. They built a very interesting knowledge graph from the news that were leaked. And they gave this knowledge graph to their journalists to look for links that nobody, or look for links or connections or shady behavior of different actors involved based on what was in those papers, as a way to drill down into interesting details faster. And since the last year, when the pandemic hit us all, there have been multiple efforts focused on creating knowledge graphs for COVID-19, be it taking the publications, be it taking the infection data. There are many kinds of COVID-motivated applications, knowledge graph applications that have been built just in the last 12 months. But for the purpose of next 10 or 15 minutes, that discussion, I have chosen to focus on applications of knowledge graphs in finance. And the discussion that we are going to have now is a synthesis of what we heard from the speakers who came to our series last year. So I'm going to just summarize and give it to you in a very concise manner how knowledge graphs are being currently used in finance. And basically we'll talk about three broad categories of applications: the analytics, the financial calculations, and financial reporting. Analytics will show the application of graph algorithms. Financial calculation will show the application of rule-based inference, and financial reporting is going to show the ontology-based inference. Okay. So here's a set of questions, analytics questions, which are of great value to financial institutions. For example, which of our clients are suppliers of a particular company are in financial trouble? In a supply chain network, is there a single company that connects a group of companies? Which startups are attracting very influential investors, etc. And I'm going to step through some of these questions and also connect the dots on how some of the algorithms we considered in the first part are applicable to answering these questions. So let's take this question: which of our clients are suppliers of company X that is in financial trouble? So to answer this question, we first of all would need information about the suppliers. And in this case, it turns out that FactSet is a commercial data vendor who curates the supply chain relationships. They are in the business of doing that, and they sell that supply chain data to a lot of other companies. You can purchase that data, and then using the techniques we considered in lecture 4, like how to create a knowledge graph from structured data, you can take the FactSet data and you can integrate that data with the internal company data, where you have complete information about your customers, right? And once you've integrated that data, then to answer this question, you would use pathfinding, right? You would basically do a pathfinding over your supply chain network to a certain distance to figure out which companies and suppliers are connected to each other. Let's take this question. In a supply chain network, is there a single company that connects a group of companies? This is a textbook example of betweenness centrality, right? If you have your supply chain network and there is one node which has very high degree of betweenness centrality, it sort of indicates that this particular company is supplying to lots of other organizations, and if anything good or bad happens to that company, you would want to know about that. You would want to stay upfront on what's going on with that particular company. Let's now consider the question: which startups have attracted most influential investors? Now, to answer this question, we would need data for which VC firm or which angel investor or private investor is funding which company. And it turns out that there is another commercial data provider known as PitchBook, who is in the business of curating this information, and they sell this information to third parties. And just like in the case of FactSet, we could purchase that data and we could bring it in, integrate it with the structured data within the company, and we could create a knowledge graph. And within that knowledge graph, if we wanted to see who are the most influential investors, we would use something like PageRank, right? We would, in that network, we would figure out which nodes happen to be most influential. Okay, and another related question you could ask is, which group of investors tend to co-invest? And to answer that question, you could use community detection algorithms, because they would take into account multiple ways these venture capital or investment companies are connected to their fundees. All right, then on that list, we also had questions like which companies are most like a given company and which company might be a good future client for us. So to answer these questions, people are using algorithms which I have not covered until now. The typical algorithms which are used for answering questions like this, they are based on graph neural networks, which are a combination of knowledge graphs with neural network algorithms. So in our Thursday's lecture, the second talk we are going to have will be focused on graph neural networks, where they are going to cover the techniques which are used for answering the questions that you're seeing on this slide. All right, so with that, let's move on to the next application, which is financial calculations. And this synthesis is based on the work that is currently being done at Intuit. Intuit, as you all know, is the maker of the TurboTax software, which many millions of people use to prepare their income tax every year. They have this Herculean job that they have to codify the relevant portions of the tax law, thousands of forms, into a usable product that is accurate and compliant, and it can be kept that way from year to year. And their job has not become easier as the time has gone along, because the tax code just keep growing, right? And so they are using a rule-based system to codify the tax law, but within that rule-based system, they are making very interesting use of graphs or knowledge graphs. And the basic idea in their application is to leverage the graph structure, which is within the rules, to automatically generate user interviews and dialogues, and then use those rules to perform the tax calculations. Now, the calculation part is interesting and it could be discussed, but I just sort of thought of pulling one very simple example from their presentation, which shows how they are using the graph structure to generate the interviews and dialogues. So let's consider a very simple example. A person is qualified for a tax benefit if the person is a resident of California and the age of the person is greater than 18 years. So given a rule like this, in English, we could code that in a rule language. And from that, they would generate a graph, which you're seeing here. And from this graph, we can make conclusions such as, if a person's age is less than 18 years, there is no way to for them to be eligible for this benefit. So if we know that their age is less than 18, we don't even have to bother asking them about their residence. Okay. Now, this is a very toy and very simple example, limited to a single rule. But imagine when you don't have one rule, but you have thousands and thousands of rules which are connected in many different ways. Then using this graph kind of connection, how these rules are connected with each other, you can figure out which interview questions you should be asking from a user. Now, I should say that some people would argue and debate whether what you're seeing on this screen is actually a knowledge graph. I mean, sure, it is a directed label graph, but in terms of capturing the semantics of the application, it is actually capturing the execution of a set of rules, right? It's not capturing the data graph, or it's not capturing the taxonomic structure of the application. But they sort of present it as a knowledge graph approach for doing tax calculations. Okay, and as I previously noted, they're using this technology as part of their products, which is at the core and heart of TurboTax line of products. With that, I'll just move on to the third and the final application I was going to consider. And this application is in the domain of financial reporting. All these financial institutions, they have certain reporting requirements. So take the example of derivative contracts. There are all kinds of derivative contracts like options and futures and forwards. And there is a complicated body of law that governs how these contracts can be entered into and how they're executed, what should happen in the case of default. And there are also fairly stringent reporting requirements. You have to do the reporting to the regulatory agencies. You also have to do the reporting to different traders who are in the business of buying and selling these contracts. So if a financial institution starts reporting information about these derivative contracts in many different formats, the job of the regulatory agencies and different trading organizations, it'll become a nightmare. So therefore, there has been a effort within the financial industry to see if there is a way they could standardize these reports. And the community has gotten together and they have developed this shared ontology known as FIBO, or Financial Industry Business Ontology. And it's a joint community effort of multiple stakeholders. And their goal is to see if they could agree on and specify the semantics of the data which is going to appear in these derivative contract reports. on this slide, I'm showing you like a snapshot from FIBO. And in this snapshot, they are giving the semantics or the definition of a call option buyer. And they're defining that a call option buyer could be either an autonomous agent, or it could be an independent party, or it could be a legal person. Exactly the kind of domain and range constraints that I was describing in the taxonomic reasoning portion of the presentation. So derivative contracts, they are just one use case for FIBO. They have many other use cases which are under development. And the hope is that in the future, this kind of standardization for data exchange is going to be more and more important. So with that, I'd like to conclude this part 2 of the presentation. We talked about how different kinds of knowledge graph inferences could be used in the financial sector. We talked about analytics operations. We talked about use of graphs for calculations and the use of ontologies for exchanging financial report data. So I'm at the end of what I had planned to say today. This is a quick advertisement for Thursday. On Thursday, we will have 2 great presentations. The first one from Martin Brevenboer, who will be telling us about how they went about efficiently implementing some of the knowledge graph reasoning algorithms on top of a relational systems. And we'll have Jiakshan Yu. He would be telling us, or he'll be introducing us to graph neural networks. So I'll stop here and happy to take any questions or engage in any discussion. We have a few minutes left. We have no questions from the audience. Mike, Narayan, Martin, unless you had something you wanted to comment on.
It was a very nice description of the inference, and I think I'm going to refer back to it again and again. It was pretty good, and also nice characterization of a variety of algorithms of applications. So that was kind of cool.
Yeah, the page rank was very interesting. Yeah. And an interesting thing about page rank is the importance of the nodes turn out to be eigenvalues of the adjacency matrix. So students who are taking other courses might be able to have a connection there.
Looking forward to Martin's talk.
So somebody is asking where can they get more information about financial application. So Narayan has a paper in the Innovative Applications of AI conference this year, where you can read about the finance application that he has been building. So J.U. from Intuit gave an excellent presentation of their tax calculation tax calculation work in our series last year. And his video is linked from our webpage. Please check it out. And then we also have plans to bring 2 new speakers who will talk about financial vertical. They've come up with different applications in the finance sector. So that I think is in our week 9. So check out our schedule and make sure that you show up for their presentation.
So we do have one question here on the Q&A, which is whether you have any thoughts on how these kinds of graph algorithms perform in huge graphs, billions of triples. How scalable are they?
So I think Martin is the right person to answer that question.
Thank you. Well, like it totally. So there is like depends, of course. Like all these different graph algorithms have different complexity. There is one of the pages I really like is a page on one of our competitors, Tiger Graph. They have a page where there's a description of all the algorithms that they implement, and all the ones that Vinay mentioned are included in that. And you can see the complexity of the algorithm explained there. And then besides that, the complexity dominates it all basically. But then After that, there are some systems that distribute and parallelize these algorithms really well. There are some systems that call out to native procedures to implement these algorithms and then parallelize. So there are some as we like to say, we want to address the brains as well as the bronze, and so you need to, of course, meet the complexity bound of the algorithm. You don't want to make it worse than it actually is, and then you need to be able to distribute and parallelize the algorithm well. So it depends on the algorithm.
Yeah. So Martin, are you planning to address that in more detail on Thursday?
I'll show a few examples of algorithms, but it's not going to be very deep about any particular complexity one of it. Yeah.
I'm really glad you guys are working on that. I look forward to hearing more about it, and I think it's a critical question. So, thanks for Sergio asking that question. I just wanted to voice a contrarian point of view. Not that is not important and so forth, but or maybe a complementary point of view, which is we keep talking about scaling for large amounts of data. But I'm also quite interested in the world of small data and how much you can squeeze out of a very small amount of data by having a very large amount of knowledge. And how does one build very large knowledge bases that are consistent and allow you to answer questions without falling into inconsistencies and missing information and so forth. And I think one of the things we don't spend enough time talking about is how to grow these very large knowledge bases that can be, squeeze a lot of intelligence out of a little data. So I think we really need to look at both dimensions of scaling and not be totally exclusively concerned with the size of the data.
Yeah, that's very true. Yeah, in fact, at least our customers are usually more interested in scaling the computational complexity than the actual data size. That's where most of the complications are. They're just not able to implement the complexity of the computation that needs to be done in different systems. And so that's absolutely true. Yeah, it's very important.
Right.
So Vinay, there are a few more questions that turned up.
Okay.
So first, a clarification on where the Intuit paper that you mentioned is.
Well, Intuit, we don't have paper, but it's on our course website. So I can share that. I can just.
Okay. So the last year's website.
Yeah. So
okay.
I'll quickly just show that. Just give me a second. Share screen. So you're seeing my screen, right? You're seeing my webpage, right?
Yes.
The course webpage. And on the course webpage, if you go to the seminar was also offered during spring 2020, click on that. And then if you go down, you'll see May 20th JU, and the video is linked right there. Okay. So everything is available online.
Cool. So there's one comment from an audience. If someone is interested in the FIBO ontology, I can get them invited to audit the next meeting of the OMG Finance Task Force, where this is being worked on. It will be the week of June 14th to 17th. And then they have the person's email, claude@omg.org.
That's great.
Yeah, that would be very exciting to see what goes on there.
Yeah, thanks, Claude, for attending the seminar.
So again, the email address is Claude, CLAUDE @omg.org.
Okay, that's great.
And then there's a question on implementation. Maybe Martin might.
Well, either of you could address. Naren, your company has been building a knowledge graph, so they're asking about how much does it cost to build a knowledge graph. So you built it, right? And I think Martin probably also has some data on the.
Yeah.
How much does it cost to build a knowledge graph?
So I'll give you the standard answer. It depends. A small knowledge graph you can just run on one computer. The problem is when you have large knowledge graphs, how do you distribute it horizontally, vertically? Do you manage it yourself? Do you get AWS or some cloud provider to manage it? So there are all these different options. Do you want something which is low latency and very rich in features, or do you want something that is very very quick to react but does not have all the data mining features? So lots of ifs and buts, and yeah, there's a whole range. So we need to be more specific about what we want to do. Martin, any thoughts?
Yeah, well, it can't really be answered in general. Yeah, like I do know that almost every big company that we talk with is working on knowledge graphs. So all, like it's really buzzing in the industry, and almost every company feel like they're potentially missing out if they're not doing a knowledge graph of their customers or whatever. And then I think typically the scope of the knowledge graph is kind of what determines how big of a project it is. Like, let's say it could be that an isolated department is building up a knowledge graph for some problem, let's say, and there's already a database that is fairly coherent, let's say, that they just want to load into a knowledge graph to do more interesting reasoning over. So that is maybe not very expensive. But like, imagine that in a big company, you're going to try to integrate all kinds of different data sources that are all inconsistent and from different systems, a lot of integration issues. That's going to be very expensive. So it really depends on the scale and the ambition. Like on the Panama Papers, let's say, like there are, you probably have seen that, is that there are Neo4j databases that have loaded those kind of data sets. And like these kind of projects are not very expensive. Like you can do that fairly quickly to load something like that. So it really depends on the quality of data and the scope of the knowledge graph. Yeah.
Okay, good. There are no other questions?
No, I think we're all done with questions.
Okay, well then maybe this is a good time to conclude today's session. Thank you all very much for showing up, and please be sure to sign in this Thursday to listen to Martin and Yorkshire.
Bye-bye.
Thank you. Bye for now.